Good afternoon, everyone, to the last in the ANFF Webinar Series. We have had 5 of these already, and this is our last one. And we are focusing on food and agribusiness in this particular webinar. This series has been very successful, and we're really pleased at the quality and the level of science that we've been able to present as enabled by ANFF technologies throughout the last 5 or 6 weeks. Today, it's no different. We have 2 wonderful speakers who are talking on very different ends of the technology spectrum, but also talking about different applications of those technologies and how they can be applied across the board in, for one of them, they're very agriculturally focused. The other is an application of a technology that can be used in the food and agribusiness sector. So as always, we will run our question and answer session through the Q&A function of the Zoom webinar. So if you wiggle your mouse down the bottom, you'll see the Q&A section. So please drop in your questions there whenever they occur to you, and I will ask them at the end of each of the talks. Any that we don't get to, we will take offline and make sure that you get an answer at some stage. We also at this point would like to again thank our sponsors who have stuck with us through this particular webinar series. They came on board to be part of our showcase, and when we moved online to this webinar series, they stayed, and we were able to provide them with some recognition of their support for ANFF and what we're trying to do with the showcase. Our showcase will still go ahead, and as of today, Queensland can now travel down to Victoria next week, and we're very excited about the possibility of getting on a plane very soon. And so hopefully in May, borders will still be open, and we will all be meeting up in Melbourne to get together and do this properly in person with many, many more talks on a huge range of science. And on that topic, if you want to look at some more of the case studies that we are producing from ANFF, please look out for the casebook. It's nearing completion, and it will be launched within the next week or so. If you want to be one of the first to have a look at the electronic version, please sign up to the newsletter and you'll be notified when it comes out. So with that all said, I will now ask Jun Zhang to come online. Now, Jun is a researcher at the AIBN at UQ. Her work involves nano biopesticides, so the ability of taking pesticides and re-engineering them to make them better, using what we know about nanotechnology and how it can enhance the efficacy of what's already there. So Jun, if I can ask you to start your talk. Jun? Yes. Oh, here we go.
Hi, Jen.
Hello,
Thank you
Jun.
so much for the introduction. I'll just share the screen, just wait a minute. Good afternoon, everyone. Thank you again, Dr. Fitzpatrick, for your introduction, and I also thank ANFF for giving me this opportunity to present my work. Today, I will talk about a sticky nano biopesticide. The title of this presentation is Silicon Nanoparticles with Spiky Surface Enable Dual Adhesion and Enhanced Performance. And first, I would like to introduce some background. Every year, ectoparasite infections cause dramatic economic loss of over $2 billion in livestock industry worldwide. Among Australian livestock ectoparasites, ticks pose a significant threat to cattle industry, and the annual on-farm cost is around $170 to $200 million, which is more than the combination of buffalo fly and sheep lice infections. Among all ectoparasite management technologies, chemical treatment is the most widely used strategy. The global volume and the value market of pesticide reached 3.2 million tons and $80 billion by the end of 2019. However, conventional synthetic pesticides we use mostly suffer from several drawbacks, including toxicity and high risk in the pesticide production process, risk to beneficial animals and human health, and being negative to environment food safety. Compared to conventional synthetic pesticide, eco-friendly biopesticide extracted from natural products provide new opportunity to combat parasites with low resistance and reduced environmental impact. As an example, spinosad is a typical biopesticide naturally derived from this bacteria, Spinosad bacteria species, and has been registered for use in organic farming. It has two majority components, spinosad A and spinosad D. Spinosad has been demonstrated high activity to pests through both contact and ingestion poison, but low risk towards mammals and many aquatic and avian animals. Currently, a lot of commercial spinosad products have been successfully developed in the market for the protection of pet and livestock, for example, sheep. In laboratory conditions, spinosad was reported to be quite stable. However, under field conditions, spinosad degraded rapidly and showed little toxicity within 1 week. This is mainly because sunlight, wind, and the rainfall can quickly degrade and dilute spinosins, which is the active ingredient. The short duration of the efficacy and the reduced potency have prevented spinosad as an efficient treatment for cattle ectoparasites such as tick, which requires repeated application leading to high costs. This is because compared to long fur animals such as sheep, the cattle has very short fur that cannot provide sufficient protection and adhesion for spinosad, resulting in serious photodegradation and poor rain fastness. Up to now, it remains challenging to develop spinosad formulation with both high photostability and high rain fastness property. Recently, nanomaterials have been employed to develop nanopesticide formulations for sustained release purpose and enhanced efficacy. In some cases, nanoparticles themselves are fabricated as toxic pesticide to ectoparasite, including nickel nanoparticles, silver nanoparticles, and some nanocrystals. In other cases, the nanomaterials are utilized as the nanocarriers for pesticide actives. Soft carriers such as polymers, lipid nanoparticles, and hard carriers such as nanoporous silica nanoparticles have all been reported to be used for the encapsulation of pesticide actives. Among these carriers, nanoporous silica nanoparticles have unique properties, including high porosity. The high porosity are beneficial for loading the active as the payload, and stable. They also have stable rigid framework, ease of synthesis, and excellent biocompatibility, which are ideal parameters for agriculture applications. Nanopesticide formulations using Mesoporous silica monoliths and Mesoporous nanoparticles as carrier have been recently reported. I have listed several examples here, all showing interesting sustainable release properties and the toxicity to target pests. This paper uses silica nanoparticles as a pesticide cloven Napier carrier, which shows good dispersity because the particle size of this nanoparticle is uniform and small, and also shows toxicity to cotton bollworm. These two papers on the right using mesostructures hollow silica here, and hollow silica nanospheres as a carrier of a tomaticide, fipronil. The controlled release of tomaticide is the focus of these two works. A recent study using mesoparasitic hollow spheres to encapsulate biopesticide, ivermectin, reveals that the siliceous shells could provide UV shielding effect and play as a useful protection to address the photo-induced instability issue of photoliable pesticide. Nanocarriers enable photoprotections to pesticide. For example, delta methrin have also been reported elsewhere. Recently, Huang and co-workers reported reduced sunlight degradation and sustained release of micro-sized polymer carrier. Encapsulated spinosad and amamectin benzoate on foliar substrate is a successful example. Besides radiation, rainfall is another natural factor that highly decreased the efficacy of pesticide actives in livestock industry. So far, developing biopesticide formulations to endure high rainfastness, especially for cattle pest control, remains highly desired. Such work has rarely been reported. Natural systems with rough surface topologies like viruses and pollen exhibit very good adhesion properties and high transmission efficiencies. For example, pollen grains with numerous spikes on the outer shell exhibit rough surfaces which enable adhesion towards hairy insect legs and mouth parts. Inspired by these natural systems, recently our group reported the preparation of a series of nanoparticles with the rough surface. A Mesoporous silicon nanoparticles with a spiky rough surface shows enhanced adhesion towards bacteria and human kidney cells. Moreover, in one of my previous work, hollow silica spheres are proven to show good skin safety in topical applications, which is ideal in the topical applications in veterinary industry. Adopting such spiky hollow silicon nanoparticles as biopesticide carriers holds great promises for developing safe and adhesive nanopesticide, contributing to high resistance to rainfall. From the reference, we summarize these challenges that biopesticides show poor post-application efficacy in the field, influenced by the photo degradation and the rainfastness and fall. So far, developing biopesticide formulations with strong adhesion to endure high rainfastness and photostability for cattle pest control remains highly desired. So here's our design to address these challenges. The mesoparasitic hollow spheres with the spiky rough surface topology will be used as advantageous nanocarrier for spinosad. Spinosad here is using as the model a biopesticide active. We expect the spiky topography would induce enhanced adhesion between nanopesticide and cattle hair, as well as the pest surface. Here we use tick as the model pest, stimulating the potency of contact poison of spinosad. To our knowledge, there are rare reports concerning the correlation between adhesive properties and the pest treatment potency of biopesticide. Furthermore, the nanocarrier is also expected to play the role for protection of spinosad molecules from UV degradation and rainfastness. So here is some of our results. Mesoparasitic hollow spheres with a rough surface, which here denoted as RS, is shown in this slide. The dynamic laser scattering result showed good dispersity of this nanoparticle. The shell of the RS were covered with nano-sized silica spikes to form the rough surface morphology, mimicking the surface topology of pollen grains. The nitrogen absorption results showing here indicate that the RS possess 15 nanometers mesopores, which is coming from the void space between the surface spikes. A control material is also selected and prepared with the exactly similar structure, but except the surface is smooth. A rotary evaporation method was used to load the spinosad into nanocarriers with the silica spinosad feeding ratio of 7:3. The products are denoted as RSSP and SSSP, but here I will just simply call them rough and smooth nanospinosad in this presentation. The field emission scanning electron microscope images shows that both nanospinosad will maintain the spherical morphology of rough and the smooth surface topology after the spinosad loading. Without using nanocarriers, the pure spinosad after rotary evaporation formed micron-sized crystals. Such crystals cannot be observed in the high magnification and the lower magnification of the two nanospinosad SEM images, indicating the successful loading of spinosad within silicon nanoparticles. The Fourier transform infrared spectra is also used to confirm the successful loading of spinosad, as the characterized peaks of the spinosad here can also be observed in the spectra of the two nanospinosad. The spinosad loading amount in nanospinosad formulations were determined by thermogravimetric analysis, shown over here. Pure spinosad exhibit almost 100% weight loss at around 570 degrees C, while both silicon nanocarriers here are showing negligible weight loss. Accordingly, using this data, we can calculate the actual spinosad loading contents in both nanospinosad, which is proven to be 30%, agreeing with the initial feeding ratio. The crystallization feature of the spinosad after loading was investigated by differential scanning calorimetry. Pure spinosad and physical mixture of spinosad and RS displayed an endothermic peak at 130 degrees C, corresponding to the melting point of crystallized spinosad. In contrast, no such peak can be observed in both nanospinosad, indicating amorphous feature of loaded spinosad. The crystalline nature of spinosad nanoparticles in nanospinosad was further examined by X-ray. By XRD measurement. It is showing that both two nanospinosad can be easily dispersed in water just by hand shaking, because the spinosad itself is hydrophobic and cannot be dissolved in water easily. So we can easily disperse in the two nanospinosad in water by hand shaking in order to apply it on cattle hide here for future tests. In order to investigate the effectiveness of nanospinosad under simulated field condition, 4 formulations, rough and smooth nanospinosad, pure spinosad, and commercial product extinosad were compared. The tick toxicity test of 4 spinosad formulations was evaluated using a modified tick larva assay, shown here using cattle hair as the substrate. The tick toxicity results are summarized in Figure A. Pure silicon nanoparticles showed little toxicity towards the tick. And the sample RSSP, which is the rough spinosad, demonstrates significantly high tick toxicity than all the other 3 formulations in the wide range of the initial spinosad concentration from 0.1 to 0.001 milligram per cattle hide piece. At a spinosad concentration of 0.1, spinosad with a rough surface achieved high tick mortality rate of 99.9%, surpassing the performance in the other 3 samples. At lower spinosad concentrations, spinosad with a rough surface can maintain its high tick mortality, while the mortality rates of other spinosad formulations had largely decayed. The tick toxicity result indicates the advantage of rough surface nanotopography of the rough spinosad formulation. To understand the function of rough surface, the adhesion amount of nanoparticles on ticks were estimated by measuring the silica content in tick larvae. The results are shown here. As shown in figures in this figure, the spinosad concentration of 0.1, the silica content in rough spinosad treated tick larva was 2 times of that in the smooth ones. This result indicates a greatly enhanced adhesion of rough spinosad onto tick body. Similar result was obtained at lower spinosad concentrations. Here. These observations demonstrate that rough surface of the spinosad formulations can have strong adhesion towards the tick bodies, as well as the cattle hair, indicating this rough surface nanospinosad formulation has the dual adhesion to both the cattle hair and the tick body, especially at the low concentration treatment. Fluorescent confocal microscopy was also employed to directly observe the adhesion behavior of nanospinozad, which are labeled with the green fluorescing probe. While focusing on the ventral surface of a tick, which means we're focusing on the outer surface of the tick, green fluorescing from both of the rough and smooth spinosad can be clearly observed here, indicating that nanospinosad were attached on the tick body surface. The confocal image of rough spinosad shows much stronger green fluorescing than that of smooth ones, stressing a higher adhesion amount. The weak blue fluorescing can be attributed to the tick autofluorescence, which is reported before. When focusing on the inner body of the tick, the images shown here, neglectable green fluorescing were observed in both groups, indicating that the nanospinosad dominantly adhere on the outer surface, the body surface of the tick, rather than being ingested. This conclusion can also be confirmed by this 3D construction of the confocal image. This data is generated from the ANFF lab. The distribution of nanospinosad on tick body were also characterized using field emission scanning electron microscopy. The results are shown here. For rough spinosad at a large number, for rough spinosad, a large number of nanoparticles were observed on the leg hair, the abdomen, and the mouth parts of the tick, both in high and low spinosad concentrations. The low concentrations shown in this column. In contrast, smooth spinosad only show several nanoparticles here, adhesion on these tick body parts at a spinosad concentration of 0.1 and almost disappeared at the concentration of 0.01. This SEM observation further demonstrates the advantage of rough surface nanotopography of introducing a superior adhesive property to tick body and leading to improved pesticide pest contact for high toxicity. In field applications, the effective duration of spinosad applied on cattle is largely affected by weather conditions, especially by the rainfall. The rain fastness test were chosen to quantitatively measure this effect. A modified spring bottle protocol was used for the test to test the rain fastness property of 4 spinosad formulations using artificial rain. The wash-off amount of silicon nanocarriers and the spinosad active component, for example, spinosad A and spinosad D, were quantitatively measured using ICP-OES and the ESIM, the mass spectrometry. The results are shown in this slide. As shown in figure A, the wash-off amount of silicon nanoparticle carriers was shown in the orange bars. The wash-off amount of rough silicon nanoparticles is much higher than that of smooth silicon nanoparticles at all rainfall strengths from 0.5 to 2.5 centimeters. At the highest rainfall of 2.5 centimeters, it is calculated that 6 times more rough silica residue remained on the cattle hair than the smooth one, proving that the rough surface topography of nanospinosad can greatly enhance their cattle hair adhesive capacity and the rain fastness property. The wash-off active ingredients were measured and divided into 2 parts. The spinosyn in rainwater and the spinosyn in silicon nanoparticles, which is shown in blue and yellow bars respectively. Under 2.5 centimeter artificial rainfall, the calculated spinosad A residue maintained on the cattle hide is for rough spinosad is 5 times than the smooth spinosad, 2 times more than the benchmark commercial product actinoside, and over 7 times more than pure spinosad. The spinosad D residue content calculated on the cattle hair show similar trend. The field emission SEM image can be used to directly observe the residue of nanospinosad before and after 2.5 centimeter artificial rainfall. After applying spinosad formulation onto the raw cattle hide, numerous spherical nanoparticles can be observed in both of the attached on the hair cuticle, in both cases of the smooth and rough nanoparticles. After the 2.5 rainfall, a significant amount of the rough nanoparticles can still be observed attached on the cuticle of the cattle hair. In comparison, smooth spinosad shows much lower nanoparticles distribution on hair cuticle, indicating most of them have been washed away by the rainfall. This huge difference between rough and smooth nanospinosad clearly demonstrates the function of rough surface for inducing high adhesion towards the cattle hide, which contributes to high resistance towards rainfall. The solar stability test of nanospinosad were conducted in natural solar radiation to simulate the field condition. Cattle hide pieces with 4 spinosad formulations were divided into 3 test groups. Group A was placed on this rooftop and exposed to both solar radiation and ambient roof temperature. Group B was placed on the rooftop with ambient temperature, but covered with aluminum foil to avoid the direct solar radiation. Group C was placed in the lab with constant room temperature of 21 degrees C and protected with the aluminum foil for the UV radiation. So this is weather, temperature, and the solar radiation intensity during the experiment dates. It shows high temperature and the radiation intensity in clear Australian weather. Residue amount of active ingredient of spinosad, spinosad A and spinosad D after solar stability test is summarized in this figure. In group A, so the left one is spinosad A, The right one is spinosad D in group A and B. All 4 samples exhibit gradually decreased spinosad A and spinosad D amount with the time increasing, while no significant spinosad degradation occurred in the group C, suggesting both solar radiation and high temperature would decompose spinosins. In group A, bearing both solar radiation and rooftop high temperature, both of 2 nanospinosad have demonstrated greatly improved spinosad protection than commercial spinosad product and pure spinosad. This indicates both of rough and smooth nanocarrier can give the protection. After 3 days test, 50% of spinosad A and 40 to 50% of spinosad D were maintained in 2 nanospinosad formulations applied on the cattle hide. This active ingredients residue is over 10 times higher over the commercial product, extinosad. This significant difference was confirmed by the t-test. These results show the silica nanocarrier indeed play a role as UV shield to provide heat and photodegradation for biopesticide molecules. As a conclusion of this work, I have developed a nanospinosad formulation with sticky rough surface with dual adhesion efficacy to cattle hide and parasite body. The dual adhesion property leads to significantly higher pest mortality towards tick as the pest than a nanospinosad formulation using nanoparticle with the smooth surface and the benchmark commercial product. The adhesion performance was further quantitatively measured using rainfastness test. Moreover, solar radiation tests revealed that the nanospinosad exhibit more than 10 times higher photostability over the commercial product. This work paves the way towards development of high-performance nanobiopesticide for sustainable agriculture and applications. At last, I would like to thank ANFF again for giving this valuable opportunity to present my work. I also would like to thank my supervisor and co-authors for this work. I thank ERC Linkage Project and the UQ Development Fellowship for the financial support, and Heringer and Eleco as the industrial partners. And thank you all the attendees for your attention.
Thank you very much, Jun. That was a really interesting way of thinking about how we use our nanotechnologies and our bio-inspired nanostructures to do something that I would never have thought of. If you have any questions, please drop them in. We have time for one, and I will kick off with this one. So you were talking about your rough silica particles. How do you actually create that roughness?
This is a method we developed before. We use a co-condensation method of I'll just change it over here. So first we use the organic silica source to create First, we use a stopper method to create a polymer, a spherical sphere, which will become the hollow cavity in the future. Then we create the silica shell over this polymer sphere. And then we use the silica source and the polymer source to do a co-condensation. Their primary particles will randomly condensate on the outer surface of the silica shell and the polymer inner. When we remove the polymer by calcination, we create the hollow core, and a part of the polymer on the outer surface has been removed, creating the void species. The remaining of the silica primary particles will form this kind of spikes. These spikes are giving the surface property as a rough surface.
Wonderful, thank you very much. Now, there are a couple of other questions, but I will leave them there because we do need to move on to Michael. So thank you very much once again, Jun.
Thank you.
So next we will move to Western Australia and Michal Zawierta from University of Western Australia, and he's going to talk to us about a slightly different way of thinking about our MEMS and how we can, by doing some really clever design, condense all of the parts required for particular ways of measuring things onto a particular MEMS chip, and in that way actually remove some of the difficulties in miniaturizing these technologies. So over to you, Michal.
Thank you for the introduction. I will share my screen. Just a second. I will be talking about atomic force microscope on a chip. I would like to thank you all supporting bodies for this work, including Australian Research Council, Panorama Synergy, and Australian National Fabrication Facility. I will start from introduction of AFM applications. So AFM is used in many fields, starting from biology, microelectronics, where we're using it. In biology, you can detect large structures like blood cells, and you can also go image really small structures like tiny molecules with dimensions below 20 nanometers. AFM is really popular in diagnostics of electronic circuits, and going to food industry, AFM is used to prepare topological images of different kind of bacteria, for example, images of E. coli bacteria, or monitoring of salmonella biofilms, where AFM is used to detect growth and see the changes over the time. And AFM is quite popular tool available on the market. Standard optical AFM readout have really high sensitivity. It can achieve high speeds of imaging, but the problem is that we cannot use multiple cantilevers at the same time, which limits imaging area. So you have to image pixel by pixel. In alternative method where we're using electronic readout, for example, capacitive readout or piezoresistive readout, we can achieve very high speed of imaging. We can introduce large arrays of cantilevers, so it allows to do imaging, high resolution imaging of large objects, for example, which is often important in food industry when imaged objects are quite large, and in electronics where we want to measure large area in limited time. And our solution allows to achieve all the three requirements, like high sensitivity, high speed, and large arrays of cantilevers in the same time. So our design is using silicon photonics waveguide to detect cantilever deflection. In that case, we have waveguide with edged grating located below the cantilever surface, and we have light coupled in to the waveguide, which then part of the light is decoupled towards the cantilever and bounce back to the gratings. Due to interferometric effect, we can detect how much position of the cantilever based on the amount of light on the output of the silicon waveguide. So as here you can see that transmitted power is changing with the change of the gap between change of the gap or cavity between cantilever and the grating. And if you start measurements in the design point, you can detect really small movement of the cantilever as a significant change of the output power of the system. And here you can see that, for example, for a separation of 7.95 micrometers, our output power is almost maximum, so it's above 80% of input power. And all the light is transmitted to from the input to the output. Most of the light which is coupled out to the cavity between cantilever and the grating is coupled back to the waveguide. In the opposite situation, when the separation is 8.45 micrometers, due to destructive interference, most of the light is disappear from the output, and we can detect that we moved from the point A on transmission characteristics to the point B. And how we fabricate these cantilevers. So our starting point is silicon on isolator substrate with etched gratings and waveguides fabricated in commercial fabrication facility. In this case, it was Leti. All the silicon photonics waveguides are visible on the optical image here. So you have input waveguide on the left-hand side and output waveguides on the right-hand side. And in the middle, there are marked interrogating gratings. And fabrication of the MEMS structure starts from blank photonics chip, on which we deposit bottom metallization, followed by sacrificial layer, top metal mirror, which is used to reflect light from the cantilever towards the grating, and then silicon nitride structural layer, which is in next step patterned to achieve to fabricate cantilever. And on the during the last step, we installing AFM tip on the end of the cantilever just before plasma release of whole structure. This last step I will present in next slides. However, this is experimental approach. It can be improved in the commercial products that to make it even easier to mass produce these devices. So in our case, we used commercially fabricated AFM cantilever tips, from which we removed tip with piece of silicon, and then we transferred it to the top surface of our cantilever. Tip was welded using focused ion beam and platinum weld to the top metal surface of the cantilever. And after that, whole structure was released to create probe. Here you can notice a waveguide marked with red color on the left-hand side, which is located exactly under the tip to achieve the highest sensitivity of the system. Additionally, there are bottom metallization which allow for actuation in the future applications. So in that case, we can electrostatically deflect the cantilever to the desired position. And light is coupled to the chip. Light is coupled using 2 single-mode optical fibers. And gold electrodes can be used for electrostatic actuation. For the tests, we use commercial AFM system. So we don't need to design scanning mechanism from zero. That's quite standard system. So it can be integrated with our probe, but this was not the scope of this work. In that case, we placed our probe in place of sample in commercial AFM system, and the sample was installed on the top scanning head, so we can image the sample. First, we did characterization of the response of the cantilever with electrostatic actuation, so we can be sure that we're operating in a properly designed point with the highest sensitivity. And after that, we could move to test sample to confirm system sensitivity. We started with silicon carbide steps, which allow to measure single nanometer, sub-nanometer height difference, and we noticed that we can achieve results similar to commercial AFM systems, sometimes even less noisy than commercial AFM systems, which we can see here, comparison of standard AFM system with our readout. We reduce amount of noise. This was in this step we did static noise measurements where cantilever was located in one point of the sample, and it wasn't scanning, so all the measured noise is noise of the system. Partially is originating from scanner head, which even in fixed position will produce some amount of noise. But in both experiments, we use the same scanner head, so the rest is noise of the difference between both two measurements is noise of the measurement system. And additionally, we did measurements of the Brownian noise of the cantilever. We can see that on these measurements that our system is short noise limited, and we are able to detect first and second resonance frequency of the cantilever using Brownian motion noise measurements. So to sum up, our integrated on-chip atomic force microscope is using silicon photonics with integrated grating to detect cantilever deflection. We managed to weld AFM tip to our cantilever. This method is mostly for demonstration of the system. In commercial products, I think we will move to AFM tips deposited using focused ion beam on top of the cantilever, which can be done really quickly, and currently available systems allow for deposition of multiple tips in the same time. And we demonstrated operation of this system using old AFM scanner inside repurposed AFM system. Okay, that's all. Thank you.
Thank you very much, Michael. That was, again, an incredible way of visualizing some of the technologies that we can't really see with the naked eye, but you've really shown us how those microsystems really get put together and actually work. If you have any questions for Michael, please drop them into the Q&A. I will start with, so this is, we know we all have AFM, so I'm sure most of us have seen an AFM or used an AFM at some stage. So what's the benefit of having one that's on a tiny, tiny little chip? How can we use that will benefit us rather than having a large system that sits in a lab?
The biggest benefit is cost of AFM. So cost without reducing sensitivity and quality of the measurements. So in that case, our AFM probe with whole measurement system in mass production will cost a few dollars, maybe tens of dollars, similar to AFM tip, but we don't need to do any alignment before measurement system is self-aligned. And whole probe with readout system, when we want to replace it, we can replace everything together. So each time, even if we measure like some samples which we don't want to contaminate the rest of the microscope, you can replace whole probe with cantilever probe with whole measurement system. So it can be isolated from measurement chamber, and in the same time we are able to fabricate multiple cantilevers on single chip and measure in multiple points in the same time. So you can achieve, for example, large area imaging in a really short time.
And when we're talking about the actual application of this kind of technology, where do you see its first killer app, if you will? So the first place that it can be applied, that it will really shine and show benefit to this kind of technology.
Many applications are not directly related to AFM itself. We already demonstrated non-AFM applications, so cantilever sensors for gas sensing, for example, hydrogen sensing. Our sensors, instead of placing AFM tip, we place sensing layer on top of the cantilever, and we were able to detect a really small amount of hydrogen in the environment. The same that kind of cantilevers can be used for methane sensor or any different gas sensors. And in that case, you can place multiple sensors on the single chip.
Okay, and so again, you're able to look at more than one thing in a very small footprint for a very small price.
Yes.
Wonderful. So thank you very much, Michael, and we'll leave the questioning there for the moment. And I'd like to thank everybody who has participated, both as a panelist and as an attendee over the past 6 weeks for the ANFF Webinar Series. I've been, as always, pleasantly surprised at the breadth of the science and the technologies that are enabled by ANFF, and how different ways of thinking are using what we're able to provide through our fabrication technologies and applying it in so many different and vast and varied ways. So once again, thank you all for your attention and for turning up. And thank you to all our panelists and our sponsors. And I'd like to finally thank the person who actually did all the hard work in getting this all together. I'm sure most of you have been hassled by Tom at some stage, but Tom is the person who has conceived of and put all of this webinar series together. And I think he's done an incredible job to showcase what it can be enabled by ANFF. So on that note, I will say thank you, and we will hope to see you all in Melbourne next May. Take care.